Hello. Controlling DC motors, as in brushed 2-wire permanent magnet motors. It's the commonest type for a lot of small projects, very many forms, from absolutely tiny things. You can get them down to 6 millimeters diameter and about that size, or even smaller, and they go up to quite massive units in industrial use. But for general hobbyist small robotics projects, vehicles, RC cars, things like that, if you're using a DC motor, hopefully this will be of interest in use. Now, this is probably the commonest basic switching circuit you'll see online. Focus. All this is 2 changeovers or relays. When they're both off, the motor has both sides connected to negative power and it's stopped and shorted out. If you switch one relay or switch, well, I'll call them relays, but they could be manual switches. If you switch either one on, then one side is then connected to power, the other side to ground. It runs at full speed. Likewise in the reverse, if you switch the other one on instead, that side is now connected to power, that side is still connected to ground. It will run at full speed in the opposite direction. Switch it off again, then it's shorted out and will stop very, very quickly, which can be a problem because as it's shorted out, the current can be quite high and it doesn't do the motor any good. It doesn't really do the switching contacts any good. But I'll demonstrate that one first. I've got a little rig set up here. Pick it up without dropping things. The battery, that's a drill battery to power these relays, because the relays are 24 volt. I'm dropping things. Now, this pair is wired as in this circuit. So the coils and switches are just purely to control the relays. I've got a couple of little toggle switches on to allow me to stick the relays on and off. So that's purely the control side. This is the switching side. It's 2 changeover contacts. That's the common, normally closed, normally open on each one. So I'm going to connect the motor, a motor, to those 2. Now for this, I'm going to use one of these little geared ones, which are readily available on eBay and such, for such as cars and robotics again. Now this motor actually has an encoder on the back, which I'm not going to use for this. I'm only using the motor wires. So that's why it's got the other wires on these. It's got magnet and Hall effect switches for feedback. But just using the 2 wires, so it's running as a straight DC motor, nothing special. So I'll connect those up here. And the red and the black are the battery, or will be. I mean, polarity isn't important, as one's forward and one's reverse, and it depends which you decide to call which. It's just a matter of keeping track of what you wanted to do after you've done the testing. So that's the motor wired to the 2 common contacts. Oops, dropping bits again. Tried to pre-wire everything to save time here, but it's just taking time now, dropping everything all the time. Oh well. Right, so motor wire to the 2 common contacts. The 2 normally closed ones are connected to the black power wire. The 2 normally open contacts are connected to the red power wire. I'll put them on here. That's a 12 volt battery. Oh, that's a Burlab type battery. It's just convenient for temporary power. Here's the insulator caps, just to wedge the wires in place. So, right, so that should now run. Make sure everything's in view. I put a little tag of tape on there so it's easy to see it turning. I'm not sure how will the camera focus. You can see that's now running for me, that's clockwise, that's that way. On the way, I don't know why it's different speed, it's just the way the motor's made. I don't know why it's different speed, it's just the way the motor's made. But you can see that way, one runs each way, and it stops absolutely dead. Now, it's the stopping bit that's the bad thing with this very simple circuit. And I don't know if I can just hold it up, so it's a little bit of a free run. Okay. A bad connection because I'm hanging it on the connector. No, it doesn't like being held on the connector. Oh well. I was going to try and demonstrate the way it kicked. It looks like that connector's a bit dodgy. I can feel the kick, but it stops so sharply that it takes a lot of current. It does actually burn the brushes and commutators to some extent every time it does that, as well as burning the relay contacts. And there's any actual visible sparking there. No, it's too small a motor to show any real sparking. But because it just stops hard, and the motor's being shorted out whilst it's running, it works, but it's not a good idea. So there are two other versions of control you can do. This is the most obvious and one of the easiest ones, which avoids all the problems. Use two-pole changeover relays. Let me just get this so it's clearer. Two-pole changeover relays on focus. That's better. Cascaded. So the motor connects to the common on that relay, which is 2 poles. If the relay is off, then it's feeding through from the other relay, so ignore that for a second. If the relay is on, then the motor is connected directly to power and ground. As I say, if that one's off, then it's being fed from the common of this relay, 2 poles. And again, if that's off, then it's just connected through to further through. If it's on, then it's connected to power and ground, but the opposite way around, because those wires are switched, these not. So it has forward and reverse. And as far as that goes, when both relays are off, the motor is connected through to these 2 wires, which you can either leave open or add a resistor to give control braking rather than the dead stop, or just letting it coast down. That's what the other 2 relays we've got here are wired for. So I'll just change the configuration to use those. So disconnect the battery and swap the motor to the other relays. The downside is you need a 2-pole switch rather than a single pole changeover switch. Get them out of the way, these in. So the motor now connects to the common of both common contacts on one relay. I haven't actually tried this and to instruct the wires on it yet, so I hope it works. We've got it right way around. Now again, that motor is quite small, low power, so the kick effects aren't so obvious, but I'll hopefully try another motor in a minute as well, after I've just checked it all works, so the kicking and torque effects can be seen better. So I'm not going to instruct the wires on this yet. So again, that's going on the 12-watt battery. Slide on that. So these are relays, but these could be two-pole changeover manual switches, one for forward and one for reverse. And when I drop things, it's pulled a wire off. Hang on a second, I've got to resolder that. Just pull the common off on the switches. Control the relays. Luckily I have got this on iron so I can rejoin it. Alright, okay. So that's working at that. Speed difference, as I say, that's down to something in the design of the motor. Just either brush wear or the brushes can be slightly out of alignment. If the brushes and permanent magnet field are slightly offset, the motor runs at different speeds in different directions. Now at the moment I have got a braking resistor in here, as shown on that circuit. So when both relays switch off, the motor is connected across a resistor. And you can see the difference in that. Before it was stopping absolutely dead as soon as I turn the switch off. Now, wrong switches. It's coasting down over about half a revolution of the wheel rather than the dead stop. If I short those two wires out across the resistor, that should emulate what it was doing before, so you can see the difference. That's the shorted out stop. That's the gentler stop with the resistor. The resistor can be quite low, but the ideal value is when the peak current it takes from the supply voltage is about the same or not much more than the motor peak current. So it's not taking excess current and unduly loading everything. Now, if I take one end of that resistor off, so it's completely coasting down. You can see the difference again. It's a lot slower stop. Just connect and disconnect that so you can see the difference. That's with the resistor, which is 15 ohms. Open circuit coasting. If that resistor was a bit lower, then it'd stop quicker. But using a resistor switched across the armature is a standard way of safely fast braking motors, even very, very big ones. Some of the resistors can be absolutely massive they're used for that, or big metal clad things, and some of them even need air cooling just to keep them cool because of the amount of power that's regenerated. Now that's another key point with motor control, with DC motors. There is nothing in principle different between a DC motor and a DC generator. If you turn the shaft of a motor, it will produce voltage. When it's being run, it produces voltage, and that's why the current drops off as they reach speed. When it's stopped, it's effectively just a resistor through the copper windings. There's nothing there to produce any back EMF voltage to generate the voltage the motor itself generates. So it just acts like a resistor and takes a lot of current, though it's still producing, of course, a magnetic field to try and run. As the speed builds up, the voltage it generates increases, back EMF that is, and then the resistance is only effectively working with the difference between the two voltages. So as the motor comes up to speed, the current drops right off until it's just enough to keep the thing running at its offload speed. And if you then add a load to it, the current will increase. I'll probably do a separate demo of that, but it's just a bit of background. That's why the currents are so important. When you first start a motor from static, it will take a lot more current, and it could be anything from like 3 to 10 or 20 times even the idle current, or the full load current, even the rated, whatever it's rated at. So you have to allow for that. So if the motor's got a running rating of, say, 1 amp, if you try and run it on a 1 amp power supply that trips out if it's overloaded, you probably find it just twitches and then shuts down, because the motor is probably trying to take anything from like 5 to 20 amps momentarily just to start up, and that current would drop off as the speed built up. And the same thing is happening in a way when you try and stop it, because it's acting as a generator. When it's at full speed, it's producing near enough the same voltage as the supply voltage. And if you short it out completely, then you're shorting that power from the motor, and all the energy is being dumped into the resistance inside it, which means a very high current spike. And that is not good. I mean, ideally, in fact, all really big motors tend to have soft start systems or speed controls, so they build up speed gradually and have a control braking. But for little ones like this, it's not practical. However, a simple modification, a simple circuit that includes a brake resistor, can give you a nice, smooth control stop without damaging the motor. Now, I'll move this onto a large motor now, one of these, which should hopefully demonstrate the effects a lot better, because there's a lot more mass and will store a lot more energy when they're up to speed. The downside is that because they're not geared, it's difficult to see the actual rotation. With this, you can at least see it spinning. All you'll be able to tell with the other one is if it's static or not which direction it's moving or anything. I mean, that is just, again, it's just strapped down to something with a cable tie, so it's not jumping about on the desk unnecessarily. I'm trying to roll about. So I'll connect this back to the relay. I'm not going to bother with the original circuit of this, because by linking out the resistor or shorting those points, I can make it work the same. I can get the wire in the terminal. I don't know what the actual current ratings or anything these motors are offhand. I can't even remember if it gives it in detail on the side that I got them from. As often, the sellers are non-technical in a lot of places, and they're just advertised based on the information they've been given by their suppliers, which is sometimes not accurate, sometimes confused. And sometimes it is accurate, but always take it with a pinch of salt if it's a non-specialist supplier. Right, so that should now run. You can see you can see the starting torque is enough to make the whole stand bounce. You can see that clearly from above, but I can stand it up like that. So okay, yeah, that should have been the other way around, really. I didn't think about that. Let me see if I can slide it back a bit. Oh yeah. So the shaft's not hanging over the end, and then I can stand it on the other end, which is probably better still. You can see it. Okay, so if I try and stand it that way up, I have to lean it on something. No. Not ideal. The stand's doing a wheelie effectively when I start it. It's actually, you can hear the click. That's the stand bucking. It's actually lifting up at that end. Or if I start it the other way, it's lifting up at that end. Due to the motor torque. And another thing is just pull the motor out. Oh no, I'll use the loose one. If I can't transfer the wires to this, and this one should hang on the wires safely for a minute, so you can see the effect of the torque. drop things and short them out. Right. This is yeah, sticking to the things because of the magnetism. I think that's pretty clear. It's actually winding the cable up with the torque it starts. That's just hanging loose, completely loose. That's due to the acceleration. Because it's being started at full power and taking stall current to start with as it accelerates. It's not so bad when it stops because it's got the resistor in. If I just twist that cheat. Oh yeah, tightens to the resistor basically, so it's shorted out. That should now give a similar kick when it stops. Yeah, you see the reaction there. It actually spins quite violently the other way when it stops. Because it's stopping so sharp and the inertia is so high. Let me go back to the other one, so you can see the flag on the shaft again. Because this is quite a high current motor, yeah, again, you can hear the second click from the stand bouncing, kicking up and bouncing as it stops at that. Now this is, as I say, a high current motor. I don't know what the running current is, but it's probably an amp or two at that. Well, or it would be under full load. Hopefully it's nothing like that when it's running light. If I put a much lower value resistor on, it should give a better braking effect. You can see at the moment that's now running through the 15 ohm resistor for braking, and it takes over a second to wind down. If I take the resistor out completely, that's now the coast speed. So as you see, it's not that much different because there's just not enough braking current to stop it sharply. That's a 1 ohm resistor. Connect that in instead of the 15. It's a bit more appropriate. That's going to take quite a high peak current, but because the motor's so big it shouldn't do any harm. And it's to be rather less than the direct short circuit current it'd be running at. Okay. So that's shortened the stop quite a bit. It no longer kicks. Kicks when it starts because it's taking such a high current, but even though that's probably taking nearly an amp initially, 10 amps initially, because it's probably producing about 10 volts, that should be taking about 10 amps just for a fraction of a second. It's not making it kick. It's still a lot less than the short circuit current. It just stops smoothly and quickly rather than kicking violently. And yeah, that resistor is hot because of the amount of energy being regenerated to it. And if I do that a few more times, it'll probably start smoking. Wrong switches again. There we go. There's so much, it's blowing the resistor because there's so much energy being regenerated. So you can see that's how the back EMF, the generator effect's working from that motor just from its own inertia. It produces a lot of power. So the next bit, one other thing. There is an intermediate circuit which you can use. A simple modification. If you only have single changeover switches or single contact changeover relays, you can add 2 diodes in series of the grounds. and a resistor across the top of them. This is something I've come up with. I've never seen it anywhere else. I don't know if it does exist anywhere else, because it is a fairly obvious modification. But what that means is there is no short circuit path between those two contacts in either direction, because there's only one diode conducting and one's not conducting to get a loop through that to short the motor. So the motor can never be shorted out directly when it's switched to stop. But the resistors will connect across, so you can still get the braking effect. If you need an emergency stop, a really fast stop, you switch them both to on, and then you get the short circuit through that loop. So you've got two stopping modes then. You've got a control stop for normal stopping and an emergency stop. You could actually put the diodes in the positive legs instead and have the resistors that side. Then the default power off state would be the emergency stop, and both relays on would be the safe stop or the control stop. Then that would give you a safe power fail mode. And lastly then, if you're going back to that circuit, the most basic one, if you redraw that slightly, so put two switches above each other rather than the one changeover, you get something like that. So effectively you've still got power from either side connected to either power or ground. You can have diodes to catch the reverse or exerce back EMF or inductive kick of the motor. Effectively, you notice that's now a bridge rectifier configuration. So those will be the AC terms of the bridge rectifier, and that's the positive and negative outputs of it. Although it needs to be fast diodes for controlling and catching small short spikes. Replace those with transistors rather than switches or relay contacts, and that's what is called an H-bridge for electronic controller motors. And that's one of the commonest forms of reversible electronic motor control. And in fact, you can buy little modules like this, which have two half-bridge dual switches on, already wired up with power terminals and control terminals, which allow you to control these either just as switches or with pulse width modulation. So the idea is that the on and off switching is happening far faster than the inductance of the motor will allow the current to change. You can control the speed smoothly. So that setup is in a pile of bits to the side of me, and it'll take a moment for me to change over to it. So just give it a minute. Needs to disconnect the existing rig. This is one of those little modules, which are readily available from, again, all the usual suppliers on eBay and actually Amazon, AliExpress, and just about every other electronics place that sells massive different parts. Now, for that one, I'm going to use, if I can find it, 1 mil or 12 volt lithium packs, because I've already got a plug on it to work with that. And I just need to connect the motor to it. Now I was testing this yesterday evening, and I'm not actually trying it with one of these big motors. I only use one of the little ones. I'll try it on one of the bigger ones, see how it works with that. So it may leak smoke, I doubt it. Obviously, you need to get the power input and the motor output in the appropriate places. The input is polarity sensitive because it's electronics, so it's negative there, positive there. But the motor polarity doesn't matter. You can switch it to suit whatever you need, depending which of the control inputs you use for positive and negative directions. That's a little PIC circuit I lashed up to control this. It's giving a double pulse width modulated output, but one's high on one half of the cycle, the other's high on the other half of the cycle. There's no dead spots or any time that everything is off with that. It's either one or the other. The only thing that changes is the ratio, the time between the two. And that pot's not in use on this test rig. The one there is controlling it goes in analog input, that's red, and the analog output's fed directly to the PWM duty cycle register. So at the moment, with that centered, it's about 50% duty cycle. So both switches are on half the time, and the cycle rate is about 15 kilohertz, which obviously is way, way faster than the motor can respond. And because of the inductance of the motor, there's virtually nothing goes through it. So it's not quite perfectly centered. I might have just been doing kick-starting. Now I've actually got the enable switch on, that's why it kicked. If the enable switch had been off, both devices had been disabled, so nothing would have happened. Switch on. Still probably too fast for the camera, but you can hear now. In fact, you can see that. The speed is controllable. Now this is oops, not that short. This is an open loop control system. This is giving a certain amount of power and a certain polarity, but it doesn't know what the motor's doing with it. That's the normal thing for the simple pulse width modulation boards, motor controllers you can buy on eBay and everywhere. If you get a complete one with a pot on it, they are a lot of the time open loop. There's no feedback. All they're doing is supplying a certain amount of power. And the thing is, that power is a lot less than the stalled power, usually. And also, the amount of power the motor needs depends on the motor load. So hopefully you can hear that. Just by touching the shaft. The motor's slowing right down, even though the amount of power being delivered to it is the same. Because as the current demand goes up with load, the speed drops. So that is a speed control, but it's open loop. And it's also fully reversible, which is the nice thing with an H-bridge. Just by changing this, no switching, no nothing, purely electronic. The speed can be smoothly varied in either direction. Now, I'm operating this in the same way as most industrial motor controls work. They're not that common now on pure DC motors, but a lot of the stuff you'll see about H-bridge circuits basically switches one on permanently and then PWM's the other one. So the two diagonal switches. So it would use one as a direction, and then the other one on its own would have PWM on it. So the motor only ever gets power in a single polarity. In most industrial equipment, both sides are active all the time, and they're switching opposite directions all the time. But it's the difference between them that matters to the average voltage across the motor. So if they're exactly 50% all the time, the average power to the motor is zero, or the average voltage across the motor is zero. If you turn one on a lot longer than the other one, then you're biasing power through it one way or the other. And I'll try and do some scope grabs to include in here to show the effect. But because the switches are always on, somehow the control is a lot smoother. You don't have to reconfigure anything to reverse. Because using one on all the time, then you've got to change to a different one on all the time. The direction changes. And not only direction, but acceleration and braking. You see, if I turn that from so it's difficult with this because it's only a pot. I haven't got any electronic means to switch that to 0 speed at the ADC, which I didn't think of that. But you can see there, if I manage to turn that back to 0 rapidly, the motor comes to 0 speed a lot quicker than it was doing when it was running on its own, and from the relays with the braking resistor disconnected. Rather than it coasting down, it stops. And that's because the inductive effects of the switching, it makes it work a bit like a buck converter, and it's actually producing voltage each switching cycle, which is captured through the diode bridge and regenerated back to the supply. So its energy is being drawn from the motor back to the power supply. Rather than being wasted as heat in a resistor, it's actually returned to the power source. And in industrial applications, that can be to the effect that things actually have to have resistors, basically big shunt regulators and resistors, that dump the excess power if there's nothing else on the same power supply using it. You can be, if you stop all the motors on the machine at the same time, so instead of one still running that can use some of the power, then it can produce massive amounts of power that have to be got rid of somehow. On a lot of older systems, it's just by switching a big resistor across the power supply to take some of that energy back and stop it overvoltaging. Newer systems can actually regenerate and put it back into the AC supply, but that's a far more complex system, but obviously nothing to do with little things like this that run off batteries. But it's just trivia. That's still not quite at 0, it's just got a tiny bit of power going to it, it's trying to run. Which is an interesting effect to feel. You can see it's acting like a one-way gate on it. If I try and turn the shaft back, it hardly moves. If I turn it forward, then it coasts like that until it stops. Anyway, that's an open loop speed control. Now, the next stage, if you wish to make something more accurate, is to use feedback. There's several ways of doing that. The simplest, in one sense, is to use the back EMF I mentioned. You can measure the back EMF voltage between the power pulses and use that to act as a motor speed reference. So the motor's acting as its own tachometer, if you like. Though that does vary to some extent with the loading and the motor characteristics. But it works, and it's quite often used for non-critical industrial motor control. The more accurate ways of doing it are add a separate tachometer that's not influenced by current or anything like that through the motor, and use that as a speed reference and compare that to the set speed, then adjust the power to hold the set speed constant. And another method is, as with this style of thing, is have some kind of encoder on the motor, so you're getting a position measurement or a turns count measurement rather than a speed reference. But by knowing how many counts you get in a certain time, you're also measuring speed. You still get distance and time, so you've got speed reference. So that's another way of getting the feedback to work. Anyway, I think that's about it for this one. And hopefully I can do an update on this with some form of speed feedback. I can, with this chip has the same logic cell, configurable logic cells as the one I'm used in the combination lock, So it can, although it doesn't formally have a quadrature encoder input, by configuring the logic cells right, you can use those to count up and down and track a count. So it works the same as if it had got the quadrature counter input, effectively so. So that can work with an encoder input quadrature, or use another ADC to measure voltage from a tacho or from the motor itself, the back EMF. Though that, with a full bridge, that needs a differential amplifier circuit, because neither terminal is connected to power or ground. So you've got to do a separate independent measurement across the motor. Anyway, I'm waffling a bit, but I hope that's given you some ideas. I'll put links to the drawing sheet with the examples on, and hopefully I can add a bit of a capture in showing the PWM voltages, so you can see what I mean by the changing duty cycles and running at 50% at no speed. Okay, anyway, thanks for watching, and please like and subscribe if you'd like to see more.